Good morning, good evening, good afternoon. Welcome back for chapter 3. Now, in chapter 2, we ended the chapter talking about quantum mechanics and the quantum numbers. So let's kind of remind ourselves where we're at. Remember that inside an atom we have shells for electrons. Inside the shell we find subshells. Inside the subshells we find orbitals. Okay? And that a single orbital can hold no more than 2 electrons. So for hydrogen, all electrons, in a hydrogen atom, all orbitals in the same shell have the same energy, and we call them degenerative. Degenerative here means have the same energy. But for all other atoms, okay, orbitals in the same subshell have the same energy. So helium, argon, xenon, silver, gold, carbon is different from hydrogen. And the big difference between hydrogen and everybody else is that hydrogen has only 1 electron, and all other atoms have 2 or more electrons. This generates a second type of electromagnetic interaction. Okay, it generates a negative-negative repulsion, as well as the negative-positive attraction that we see in let's see if I can get this to roll up for me. Okay. I am really not good at using the screen, guys. Okay, let me walk over here and fix the screen. I'm definitely not good at this. Now, guys, let's go back here. So, in a mini electron atom, in a mini electron atom, not only do we have to deal with nucleus electron attraction, plus minus attraction like you see in hydrogen, but you also have to deal in electron-electron repulsion. So the size and shape of the orbital has a role to play in how the repulsions and attractions work together to give rise to the energy state for the electron in a specific orbital. So let's talk about how the energies of orbitals stack up and how they compare atom to atom. One of the first things that controls the energy level for an electron in the atom is the atomic number. The atomic number Z tells us the number of protons in the nucleus. And in general, the higher the Z atomic number, the lower the energy of an orbital, any orbital. So a 1s orbital in lithium is going to have a different energy value than a 1s orbital in carbon. Carbon has more protons in the nucleus, so it's going to have a lower energy for its 1s orbital than lithium does. Okay? Now when I talk about a lower energy, well, now let's not worry about it. Just it's a lower energy. Now, if we compare a 1s orbital for a hydrogen atom with a 1s orbital for a helium 1 plus. A helium 1 plus is a cation. Remember I defined cations earlier. A cation is a positively charged particle. So if we have, if we look at the s orbital in hydrogen and s orbital in helium 1 plus, the s orbital in hydrogen is higher in energy than the s orbital in helium 1 plus because the helium 1 plus has a bigger nucleus. So the Z number affects the energy of an orbital. Okay? Inner electrons, those in smaller shells, having lower in values, also affects the energy of an orbital. because they interfere with the attraction between the nucleus and the electrons in these larger orbitals. So electrons in closer to the nucleus are going to affect things that are further from the nucleus on average. Okay, so let's look at this. Now, this action of the inner electrons for the interaction of the outer electrons with the nucleus is called shielding. Okay, so it's the blocking of the attraction between the nucleus and other electrons that are further out. The actual attraction an electron feels in a larger orbital is called effective nuclear charge. What does the charge of the nucleus look like from the point of view of an electron that is traveling further out from the nucleus? It's always less than the actual nuclear charge because you have that interference effect, okay? Electrons in inner orbitals have a shielding effect, an interference that decreases the attraction between the nucleus and electrons that travel further out. This decreases the effective nuclear charge. Along with the effect of inner electrons, the shape of the orbital also provides, well, electrons in the same shell can provide some electron-electron repulsion, which has a tendency to keep, to change the energy of the orbital. So let's look at a pretty picture. Now, guys, let's say this is a 3-proton nucleus, plus 3, and there are 2 electrons in the 1s shell. We've got 1 electron out here that's in 2s, okay? Now, this is really simplified because remember, this electron can move into this space too, but it spends some time out here. These 2 electrons in here are interfering with the interaction of this electron with the nucleus. Because it interferes with the interaction with the nucleus, this electron's experience of the nucleus is reduced. In this diagram, it says that the net, go up, no. Why did it go all the way down? Okay, let me get it back to where it needs to go. Guys, I'm learning how to use this screen, and it's not being nice to me. It jumped me all the way down to the bottom of the set of notes. That is definitely way too far. Okay, we're right here. So I gotta be careful. Okay, so these inner electrons interfere with the interaction of that electron with the nucleus. It reduces the net charge that it feels from the nucleus. So in this diagram, they're saying that this guy has an effective nuclear charge of 1. Well, that means I've only got 1 juggler on stage. These guys see 3 jugglers on stage. It interferes, okay? So to experience the full +3 charge, it would have to be in closer to the nucleus. So how much charge an electron in these outer electron orbitals feel depends on how big, of course, that orbital is, and it also depends on something called penetration. Okay? Now remember that orbitals overlap. And that outer electron, the electron in the outermost shell, or the outer shells, is not kept from going in close to the nucleus. It gets to move in and out from the nucleus. But the time that it spends in close to the nucleus is going to play a role in how much pull it feels from the nucleus. The greater the electron density is closer to the nucleus, for an orbital, the greater the interaction between the nucleus and electron, and this is referred to as penetration. The more penetration that an electron has in close to the nucleus, the less shielding it experiences. Okay, now I'm gonna draw a picture here to kind of help us out. Okay, so my nucleus here is my black dot, and it's way oversized. Okay, so here's my 1s orbital, and the 2 electrons in there, they are moving around in this whole space. Okay, if I put an electron in a 2s orbital, it's going to be moving in all this space. But remember, it has some dead zones. So it has kind of a dead zone here. So I'm going to draw kind of a double circle here. So it's in all of this space, and it's in here. Okay, so it's got some penetration in next to the nucleus. If I now throw in just one 2p orbital, 2p orbital looks like this. Now if I compare it to 1s, you can see that it has a lot less penetration. There's less volume of this orbital in close to the nucleus. The smaller the volume of the orbital is in close to the nucleus, the less penetration it has, the more shielding it experiences. Okay? Let me roll up the screen and we can look at some graphs. 5 orbitals, that's 10 electrons max. And the F subshell has 7 orbitals, and that is 14 electrons max. Remember, the S is L equals 0, P is L equals 1, D is L equals 2, and F is L equals 3. We don't have to worry about anything above L equals 3 in a ground state atom. Okay? Now helium has 2 electrons. They're both going to go into the 1s subshell because the 1s subshell has 1 orbital and can hold 2 electrons. So we get 1, 0, 0 plus a half, just like hydrogen, and then we go 1, 0, 0 minus a half. Now I have 2 electrons in the 1s orbital in helium. And now the 1s orbital is full. Okay? If we move on to atomic number 3, we have lithium. Lithium has 3 electrons. So I repeat what I did for helium. 1, 0, 0 plus a half. 1, 0, 0 minus a half. Now the 1s subshell is full. Max 2 electrons. That means I have to go to the second shell, 2. Now if we look at our diagonals, okay, 2s is next. So that tells me that I have a 0 here and a 0 here, and we always go with plus a half first, up spin. So here's the set of 3 quantum numbers for the 3 electrons in lithium. Okay? The next element up is beryllium. 4 electrons. I take everything in lithium, copy it over, and then I'm going to add 1 more. So I have 1, 0, 0 plus a half, 1, 0, 0 minus a half, 2, 0, 0 plus a half, and 2, 0, 0 minus a half. Because the s subshell has 1 orbital, it can hold 2 electrons. One with up spin plus a half, one with down spin minus a half. Okay? Now, things get more entertaining when we get to the next element. Okay? Our next element is boron. And boron has 5 electrons. So I'm going to have the 1, 0, 0 plus a half, the 1, 0, 0 minus a half, the 2, 0, 0 plus a half, 2, 0, 0 minus a half. There's the first 4. After 2s in energy comes 2p. So I have 2, 1. Now the number here could be minus 1, 0 or plus 1. It doesn't matter which one you choose. They're degenerative. They all have the same energy. Out of habit, I usually go minus 1 first, but a 0 there or a 1 there would still be fine. And plus a half, we usually go with plus spin before minus spin. Okay, so those are the 5 electrons in boron. Now, after boron comes carbon. Carbon has 6 electrons. Okay? So 1, 0, 0 plus a half, 1, 0, 0 minus a half, 2, 0, 0 plus a half, 2, 0, 0 minus a half, and I have 2, 1 minus 1 plus a half. Now comes an interesting question. I've got the 5 electrons in. I just copied what I had for boron. I need to put in the 6th and final electron. But now we have choices. In the p subshell, there are 3 orbitals. Okay? P subshell, 3 orbitals. So this next electron has a choice. It can either go into the orbital that already has an electron and share a room with this electron, or it can go into one of the other p orbitals that is completely empty. Okay? The choice that the electron makes is actually to go into a separate orbital. So it goes into another one of the p orbitals and gets that orbital all to itself. This is referred to as the Pauli exclusion principle. Okay, the Pauli exclusion principle says no 2 electrons in the same atom can have the same set of 4 quantum numbers. Well, no, I've already told you Pauli exclusion principle. This is Hund's rule. Okay? Hund's rule says that when orbitals of equal energy are available, okay? When orbitals of equal energy are available, electrons choose to go into orbitals one at a time before they double up. Okay? So, electrons go in one at a time before they double up. Now, I'm going to show you this again with Hund's rule in just a second when we talk about box diagrams. Okay, now, if I got up to something like, tungsten, that has 74 electrons. That would be 74 sets of quantum numbers that we'd have to write. And let's face it, chemists don't like to write any more than they have to. So we want to simplify how we represent the quantum numbers for an atom. And our first step to doing quantum numbers in a simple way is something called a box diagram. Okay, now let's talk about a box diagram and then we're going to do some box diagrams. Okay, a box diagram it's also called an orbital diagram, and each orbital is represented by a box. It's labeled with its shell number and its subshell letter, its common name, and it's placed in order of increasing energy. Boxes are grouped according to subshell. Arrows are used to represent electrons, with up arrows representing plus 1/2 spin and down arrows representing minus 1/2 spin. So we're going to do the box diagram for hydrogen through carbon. Okay? So let's come all the way back over here. So if I look at hydrogen with its 1 electron, I draw one box, label it 1s, and put an up arrow in it. We look at helium with 2 electrons. We start with 1s, and it's got 2 arrows. We go to boron with 3 electrons. Start by drawing 1s. It's filled at 2. Then I have to go to the next energy up, which is 2s, and it gets 1. Now, from this, I can go back and give you quantum numbers, okay? But this is much quicker and easier to draw. Excuse me. This is supposed to be lithium. And after lithium is beryllium. 4 electrons. 1s is first. 2s is now filled. So hydrogen, helium, lithium, beryllium. Next is boron. Okay, it's got 5 electrons. 1, 2, fills the 1s. Next in energy is 2s. Next in energy is 2p. 2p has 3 orbitals. That last electron can go into any one of the boxes. We now move on to carbon with 6 electrons. Okay, we've got 1s, 2s, and I know I need to draw 2p because boron used 2p. So 1, 2, 3, 4, 5, 6. Okay, now one of the things that box diagrams do for us, besides getting us out of writing all those sets of quantum numbers, is that it allows us to see unpaired electrons. Hydrogen has 1, helium has none, lithium has 1, alive. Beryllium has none, boron has 1, carbon has 2. That's going to affect the behavior of the element when it gets ready to bond. Okay? And we can see Hund's rule in action here in carbon. The 2 electrons in the p subshell are in separate orbitals. So if we move on to the next element, nitrogen, which has 7 electrons, okay? 1s, 2s, 2p, 1, 2, 3, 4, 5, 6, 7. Okay? Nitrogen, in its unbonded state, has 3 unpaired electrons. We move on to oxygen with 8 electrons. I have 1s that has 2, 2s that has 2, 2p has 1, 2, 3, and now one of those has to be paired up. Doesn't matter which one. I usually start from the left and work my way right, but you don't have to. So you can see that oxygen has 2 unpaired electrons. Okay? After oxygen comes fluorine at 9 electrons. One s, 2s, 2p, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 unpaired electron. And when we get to neon with 10 electrons, I've got 1s that has 2, 2p is going to have 6. Neon has no unpaired electrons. That's going to be important in the way that neon behaves. Okay? Now, box diagrams are a big improvement over writing sets of quantum numbers. It's a big improvement. But we're going to move on to something called a term electron configuration. Let me scoot you back over here for a sec. A term electron configuration, or sometimes just called the electron configuration, is made up of terms that give a shell, subshell, and as a superscript number of electrons in the subshell. So we use the shell number, the subshell common name like S, P, D, and F, and then a number of electrons in that subshell. We've lost a little bit of the detail, but we can always pull the detail back out if we need to. Okay? So we could go from a term electron configuration back to a box diagram and go from there back to a set of quantum numbers if we need. We're losing some information, but it's information we can readily re-extract if we need to. So we're going to write some term electron configurations. And we're going to use the Aufbau principle. Okay? Now guys, in a normal situation, I have 3 boards to run around the room writing on. I don't have that right now, so bear with me as I keep sliding you around to look at things. So I'm going to write term electron configurations for everybody up through neon. And you have seen me do the box diagrams. Okay? I would normally put them all together, but I don't have enough room. So hydrogen with its 1, its electron configuration, we would say is 1s1. Okay? Helium is 1s2. Lithium is 1s2, 2s1. Okay? Beryllium, 1s2, 2s2. Now look at that box diagram. Okay, hopefully you wrote it down or, scan backwards. Remember the box diagram here is 1s and it had 2 arrows in it, and 2s had 2 arrows in it. So you can see 1s2, 2s2. Okay, now boron, 1s2, 2s2, 2p1. Carbon, 1s2, 2s2, 2p2. Nitrogen, 1s2, 2s2, 2p3. Remember, 1 electron, 2 electrons, 3 electrons, 4 electrons, 5 electrons, 6 electrons, 7 electrons. 2, 4, and 3 is 7. And then we have oxygen with its 8 electrons is 1s2, 2s2, 2p4. Fluorine with 9 electrons is 1s2, 2s2, 2p5. And then neon is 1s2, 2s2, 2p6. Okay. Now, this is much simpler than the box diagram. So we're going over things and we're improving how we write it. We're condensing things down. Okay? All right. Now, I want to show you a couple of things and we're going to relate it back to the periodic table. Again, I'm struggling a little bit because I'm working with limited space. Somewhere on a sheet of paper, as you're watching these notes, you ought to have this written down, the diagonals. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 7s, 7p. I'll put 6d in here. Okay, now I'm going to draw the down arrows. We always start here. 1s is always lowest in energy. And then it's 2s. And then it's 2p, 3s. We're just following the diagonal lines. 3p, 4s. 3d, 4p, 5s. 4d, 5p, 6s. 4f, 5d, 6p, 7s. And then 5f, 6d, 7p. Okay, so you kind of want to always have that to the side to kind of help you. Now, I'm going to look at some elements that are in columns in the periodic table. Namely, we're going to look at the configuration, let's say, of magnesium and calcium. Then I'm going to look at aluminum and gallium, argon and krypton, and then we're going to do like zinc and cadmium, okay? So let's look at magnesium and calcium. Magnesium and calcium are in the same column on the periodic table. Now we're going to look at why they're in the same column. Magnesium has 12 electrons, calcium has 20. So 12 electrons, 20 electrons. So if I start out at the lowest position first, 1s, it'll hold 2, and then 2s holds 2, that's 4. 2p will hold 6, that's 10. I have 2 more electrons, 3s is next in energy, and it'll hold 2. So the electron configuration for magnesium is 1s, 2s, 2p, 1s2, 2s2, 2p6, 3s2. Okay? When I go to calcium, I've got 1s2, 2s2, 2p6, that's 10. 3s2, that's 12. 3p6, that's 16. And after 3p in energy comes 4s. Let's see, that's 10, 16, 4s, that's 2, 2s2, that's 10, 12, 18. And 2 more gives us 20. So I want you to notice here that magnesium ends in an s subshell with 2 electrons. Calcium here ends in an s subshell with 2 electrons. Okay, if we move on and we look at aluminum and gallium and then argon and xenon. Aluminum has 13 electrons and gallium has 31 electrons. Aluminum, then I go 1s2, 2s2, 2p6, 3s2, 3p6, that's 18, 4s2, that's 20, well excuse me, I went overboard. 1s2, 2s2, 2p6, that's 10, 3s2, that's 12, 3p1, it's aluminum. I was headed toward gallium, I apologize. Gallium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, that brings me up to 20. Now, after 4s in energy comes 3d. So 3d is next, it'll hold 10. 20 from 31 is 11, so I can fill the 3d subshell up, and then after 3d comes 4p in energy, 4p1. So notice here that aluminum and gallium both end in 4p1. And that's because, and that's the reason why they're going to end up in the same column on the periodic table. Okay, so let's look at a periodic table. I think you're starting to get the idea. Okay, get you centered here again.